All right, today we're tackling a concept that is absolutely essential if you're working with tree data structures, level order traversal. If you've ever found yourself needing to scan through a tree one layer at a time, then you are in exactly the right place.
So just picture a binary tree in your head. Now, what if I asked you to read every single node in that tree, but in a very specific way, kind of like reading a book? You start at the top, read that whole line from left to right, then move down to the next line, and the next, all the way to the very last page. That's the challenge we're going to solve.
And this method has a name, of course, level order traversal. Now, if you've ever dealt with graph algorithms, this might be ringing a bell. That's because it's pretty much a direct application of breadth first search, BFS. Honestly, in the world of trees, level order traversal is basically just what we call BFS. And here is why you really want to pay attention. This isn't just some abstract computer science theory. No way. This question comes up in technical interviews all the time. So if you want to crush those interviews, you've got to have this down cold.
Okay, before we even think about writing a single line of code, let's just build a solid intuition for this. Because trust me, the core idea is actually super simple once it clicks.
Let's think about it with an analogy. Imagine you're in line for a movie. The first person who gets in line is the first person who gets a ticket, right? It's a classic first in, first out system. We're going to use that exact idea. The very first thing we do is take the root of our tree and put it in line. So here's how that plays out, step by step. First, the root node gets in line. Then we process that node at the front. Now here's the key. As we process it, we find its children, left and right, and we tell them, hey, you two get in the back of the line. And then we just repeat. We take the next node at the front of the line and do the exact same thing. It's just a cycle. And that first in, first out property, or FIFO, that is the absolute key to this whole thing. See, because we process all the parents on one level before we ever get to their children, who all got sent to the back of the line, the algorithm naturally forces us to go level by level. It's a really elegant guarantee. All right, now that we've got the intuition locked in, let's translate this logic into some actual code and look at the details that really make a difference. Okay, here's a pro tip, especially for you Python developers out there. You might think, oh, I'll just use a list for my queue. Don't do it. Popping from the front of a list is incredibly inefficient. It's an O of N operation because every single other element has to shift over. The right tool is a dequeue from the collections library. It's designed for this exact job, giving us that beautiful O of 1 performance. Now, if you need to group the nodes by level, like in a list of lists, this one line of code is the secret sauce. Before you start processing a level, you take a snapshot. You ask the queue, how many nodes are in you right now? That number, that level size, tells you exactly how many nodes are on the current level. Then you just loop that many times. It's like putting up a little velvet rope in the line. So inside that loop, for each level, it's just a simple 3-step dance. 1, dequeue. You pull a node from the front. 2, process. You do something with its value. And 3, enqueue. You add its children to the back. That's it. You just repeat this little dance for every node on the level. And of course, a production-ready solution has to handle the weird stuff, right? The edge cases. What happens if the tree is totally empty? Or if it just has one node? What about a really long, stringy tree that's basically a linked list? A great implementation handles all of these scenarios without breaking a sweat. All right, time to talk performance. You knew it was coming. In any interview, you've got to be able to analyze the time and space complexity, so let's break it down right now. And the good news is, it's pretty straightforward. The time complexity is O of n, where n is just the total number of nodes. The space complexity is a little different. It's O of w, where w is the maximum width of the tree. Let's dig into why. So why is the time O of n? It's really simple when you think about it. Every single node in that tree gets put into our queue exactly once, and it gets taken out exactly once. We're doing a constant amount of work for each node. There's no repeated effort. It's perfectly efficient. Okay, so what about space? The extra memory we're using is almost entirely for that queue. And the question is, how big can that queue get? Well, it's going to hit its absolute peak size when it's holding the widest, most crowded level of the tree. We call that maximum width, W, and that's our space complexity, O of W. So what does O of W mean in the real world? Well, in the best case scenario, you get a tall, skinny tree, like a long chain. In that case, every level has only one node. So the width, W, is just 1. That means the space complexity is constant, O of 1.
The queue never has to hold more than a node or two.
But on the flip side, the worst case is a short, wide, perfectly complete binary tree. On a tree like that, the very last level can hold roughly half of all the nodes in the entire tree. So in that situation, the maximum width, W, is actually proportional to n, making our worst case space complexity O of n. Okay, we've totally mastered the algorithm itself. But here's the best part. Level order traversal isn't just one solution to one problem. It's a fundamental pattern, a key that unlocks a whole bunch of other problems. Once you get this pattern, you can solve all of these problems with just tiny little tweaks. You want to do a zigzag traversal? You got it. Find the right side view of a tree? Easy. Just grab the last node on each level. It's an incredibly powerful building block. So let's wrap this all up with your interview cheat sheet. If this question comes up, here are the 4 things you need to nail. 1. Explain the core idea with the queue and its FIFO property. 2. Justify using a DQ instead of a list for performance. 3. State the complexities. O of n time, O of w space. And 4. Show you really know your stuff by discussing the best and worst cases for space. You hit those 4 points, you're golden. And there you have it. Level order traversal demystified. The logic is simple, the code is efficient, and now you know how to analyze it like a pro. So the only question left is, now that you have this powerful tool in your toolbox, are you ready to go build something cool with it, like that right side view?